Okay, here's the video on direction fields. Let's look at 16 on page 8. This is part C, and there's my differential equation. Before I do anything with this, this is an equation. It has a solution. What is the solution? I've noticed that by the notation, y has to be a function of t. So before we do anything else, let's recognize what kind of an answer we're going to get to this. It has solution. Well, so if y is the dependent and t the independent variable, y is some function of t. There's a function of t where if you took the derivative with respect to t, it would be equal to y, the function minus 2. That's all that says. Okay, so the direction field. Here's what we do when we create the direction field. It gives us some broad overview of what the solution is like. Okay, the solution to this exists somewhere over here on the YT plane. Alright, it's there somewhere. And I'd like to tell you how it must behave. I can do that by looking at this equation and noticing it says dy dt is y minus 2. What's dy dt? It could tell us how y changes when t changes. It can tell us also the slope of this. The derivative is the slope of this curve. This is how the slope of the curve behaves. The slope of the curve depends on y alone. Now, since the slope of the curve has such a simple dependence, we can do something like this. Just over here, express how dy dt varies with y. It should be easy for you to notice. I mean, if y is 2, on that field where y is a function of t on the yt plane, anywhere that y is 2, the slope of the curve has to be 0. That's what that says. 2 minus 2 is 0. dy dt is 0 in that case. If y was bigger than 2, if y was 3 or 4, it would be plus. But there's more to it than that. The further y gets from 2, the more positive or steeper the slope of the solution curve is. And if y was less than 2, if y was 1 or 0, the slope would be negative. But the further I get from y that way, the more negative the slope becomes. Alright, now so what if that's what the solution curve has to do? Let's draw a bunch of field lines to express that. Let's start over here. Suppose that's 2. I'll put all these horizontal dashes right there. And I'll tell you that's at y is equal to 2. And what's the reason for drawing them horizontally? Well, because that's anywhere here on the graph of that solution curve, the curve must be flat, it must be horizontal. That's what this means. And what if you went above that? Wherever the solution curve might be, slope would be positive. It would just be barely positive at first, and it would get more positive or steeper. So that makes me envision something like this. Notice how I went above 2 a little bit, and I draw these field lines that just express that it got a little bit steeper. And what if I go above that? Well, it gets even more steep. So I'm tilting my ruler, increasing the slope as I go further above y is equal to 2. So something like that. I mean, you could keep drawing it, but if you're drawing this for yourself, there's only so much that you can draw. That's good enough. That covers this part right here. Beneath it, so the slope's negative, but it's just barely negative when you're barely under 2, and then it gets steeper in the negative direction, so that would have to be something like this. At first it's just gradually going down. If I go even further below 2, then it gets even steeper in the negative direction. And so from that you get an idea what the direction field looks like. So yeah, whatever the solution is, the solution, y is a function of t, is here somewhere, right? It has to abide by these field lines. It imposes itself and abides by every single field line that's in my direction field. Okay, so that's how you draw a direction field. I want to do something to help us understand this a little bit better. Say I give you this question on top of that. Can we solve this differential equation? dy dt is equal to y minus 2. Alright, so say I ask you that. Say I also give you an initial condition that y of 0 is 1. What would that do for us? You know, say that we do solve it. What does the initial condition do? It tells us that that point right there is on the solution curve, and that curve also has to abide by field lines that are basically like so. So it almost looks like it'd have to be some kind of negative exponential that contain that point. Let's see if we can verify that. How do you solve this? This is a separable differential equation. You can separate the variables. We can get y and dy on one side, t and dt on the other side. If we do that, we get 1 over y minus 2 dy. That's easy to integrate. That won't be a problem. And then we would just get, I guess I'll put 1 dt. Yeah, so y and t. Integrate the left with respect to y and the right with respect to t. So what are we going to get? Natural log y minus 2. And over here, I'll say t plus, and I'll throw the constant over here on the right. So what's the solution? What are we trying to get? Y to be an explicit function of t, and I can do that from here. I can say absolute y minus 2 is e to the t plus c. What's that? That's e to the t times e to the c. That would be, well, I guess a constant factor of some kind. Alright. So like that. K is e, a constant to the c power. I'll just rename it. I'll put it there. I can also remove the absolute value. I've never told you why yet, but I can. And so I'll also do that. I'll explain later why that doesn't matter, but I get here. And then I get my explicit solution. It's k e to the t plus 2. Okay, well that would be the general solution. No, k is a constant. If y of 0 is 1, I can turn a general solution, general meaning that any solution to that takes this form. I can turn the general into the particular, and well, okay, so I get 1 is k plus 2. If I did that, I would find k to be negative 1. So what's the particular solution? Y is equal to negative e to the t plus 2. Okay, that's the particular. That's the solution that abides by the general, but has this particular point on it, which you can verify if t was 0, y would be 1. Okay, so how does that belong over here? An exponential falling like so with an asymptote of 2. Well, that's, even though, I'd have to draw field lines everywhere to get a complete direction field, this is enough to tell that that does belong over here. Something like that. Alright, so it fits the direction field. It abides by everything that you see there, and that's what we expect. Any solution would do that. Okay? Now, some of the questions in the book ask us, what happens if, just from the direction field, can you say what happens to y if t goes to infinity? Well, it depends on what the initial condition is. I guess if the initial condition contains some point up here, any curve that contained that would have to rise. If the initial condition contains some point down here, any curve that satisfied that would have to fall. So, y would go to infinity or negative infinity, or if the initial condition was on the line y is 2, well, the slope is 0 there, so you remain horizontal all the way. You don't have the ability to deviate from the line if the initial condition puts you on the line.